I'll be talking about low overhead tracing in Linux environment and how we can use eBPF to deploy tools into Kubernetes and clusters. My name is Gaurav Gupta. I work in SAP as a developer. So today, I'll be talking about eBPF, what is eBPF, and how we can use eBPF to develop our own tools, which can then be deployed in even in production environments for monitoring and tracing purposes. So eBPF takes its name from BPF, which stands for Berkeley Packet Filter. This is a technology from 90s which was developed to filter packets in the kernel. It was used by TCP dump and Wireshark to filter the packets based on certain criteria like IP or the port name. This has been termed as the next Linux superpower. Um, the BPF was extended into various other systems. That's why the name extended BPF. So what is BPF? BPF is part of the Linux kernel. And as we see here, BPF is a Linux kernel virtual machine which runs inside the kernel. And which helps user to attach handlers or programs to kprobes, uprobes, or trace points and perf events. So user writes BPF program in the user space and compiles it to BPF bytecode and loads into the BPF kernel machine, kernel virtual machine through verifier. Verifier checks for the validity of the BPF program that is submitted by the user. There are certain things you're not allowed to do in BPF programs. For example, you can't run loops in BPF programs. And to read any of the kernel variables, you need to first copy it to the BPF stack so that there are no security holes in the code. Also, it has its own JIT compiler, which makes it really efficient to run in the production environment. So it reduces its own overhead when this program is run in to trace functions of kernel or the user space. BPF system also provides kernel maps, BPF maps, in which data can be aggregated into the kernel itself, which can then be read from the user space asynchronously at particular interval of times. So that way you have, that way not all the data is copied to the user space, only the summary of the data can be copied to the user space, further reducing the overhead of the tracer tools. Some of the tools that use eBPF are like SecComp, which uses eBPF to sandbox applications, to sandbox the applications, and sorry. So it helps to run third-party applications in safer manner by restricting some of the syscalls that the process is allowed to do. Another good example is Cilium, which provides networking solutions, which also provide security load balancing to application containers. This here is a link provided, is a page on Kubernetes blog, which talks about different eBPF projects and how they can be used in Kubernetes. This is a screenshot from ViewScope. Here we see that there are different pods, and the edges that we see here are the connections between different pods. These edges can also be drawn using eBPF program by tracking or tracing the socket connections that processes or pods are making. Now, writing these BPF programs can be hard. So there are tools that help us write BPF program in higher level languages like Python, Lua, or C++. And so in the image that we saw earlier, one of the tools that we'll be talking about is BCC, and in the image that we saw earlier, BCC is the user space component, which provides us the front-end libraries through which BPF program from the higher level languages can be compiled into BPF programs. It also provides helper functions to read the maps or the data that is aggregated from BPF code into the user space asynchronously. So these are some of the tools that are already available as part of BCC toolchain. As we can see here that almost all the Linux stacks are covered by these tools. So for example, this OpenSnoop, we can use to track the files that are getting opened in the system, or BioSnoop can help us get details of the I/O operations happening, disk operations happening in the system, and it can tell us details like which process is trying to do the I/O and what is the latency that that particular process is seeing when doing the I/O. Similarly, there is a tool profile that is available, which can tell you the on-CPU profile of different processes, which translates to how much process is consuming how much of the CPU. Similarly, there is ext4 slower, which tracks the ext4 operations and shows the latencies of those ext4 operations. There are various use cases of eBPF. For example, BPF filter. So Linux community is working on replacing the in-kernel implementation of IP tables and replace it with BPF filters. So the network packets can be dropped based on the IP table rules early into the network chain. Similarly, BPF programs can also be used for DDoS mitigation or for checking security vulnerabilities. Today, we'll be focusing on security aspect and the observability aspect of it. So using eBPF programs, we can track new processes that are getting spawned in the system. And also, we can monitor the PTY or the TTY or the PTS devices that are opened when some user takes a shell login, for example. And for observability, eBPF programs can also help us to get the function latencies at the function level, and also helps us in monitoring hardware and software events. We can also generate on-CPU and off-CPU profiles with very little overhead of the BPF programs itself. This is a typical example of BCC code snippet, which is taken from one of the tools available in BCC toolchain, which is called func latency. So here we see that we are attaching a kprobe to the function VFS read. We register a handler trace func entry, which is called whenever VFS read is called. This function gets the PID and the timestamp at which this was called and stores it in a associative array into the BPF map, which is in the kernel itself. This tool also registers a return probe, and the handler is trace func return, which is called whenever the VFS read returns. What this function does is that it takes the PID, it looks up that PID into the storage map, which was saved by the entry function, and it finds out the delta, and then it has the latency of the function that was seen by VFS read. And it further stores in another map provided by BPF, which can be read from the BCC user component asynchronously after every particular time interval. So here we see a typical output of the code that we saw earlier. That code saved the data in a histogram, which is also provided by BPF in the kernel. So here it's very easy to visualize that around 200 calls fell into the bucket of 500 nanosecond to 1 millisecond of latency. Another output example from another tool called VFS-stat from the same toolchain is which shows the number of VFS operations happening per second. And the same tools also can provide output in the format that is understood by Flame Graphs tool, which was developed by Brandon Gregg. Flame graphs are a great way of visualizing stack traces. This is an example of off-CPU flame graph, which shows the Java stack of a process. The vertical columns that we see here are individual stack traces. So each column here from the top is a stack trace. And the x-axis is nothing but these stack traces are just sorted alphabetically, but the width of each column shows or is proportional to the time taken or the time a particular stack was scheduled off the CPU. So for on the CPU flame graph, the width will denote how much time it spent on the CPU, and for an off CPU flame graph, it denotes how much time it spent off the CPU. So here, for example, we can see that the thread 1, which was the heavy thread, spent some time off the CPU, around 50% of the time. And for proportionally this much amount of time, it was looking for memory. The thread 2 also was scheduled out mostly because sleep was called, and through this we can easily visualize that which part of the code, which thread is not optimized. Here we see the garbage collection stack also here. So details like this we can get from BPF tools with a very low overhead of its own. eBPF can also be used with the containers. eBPF programs can be attached to C groups. One of the projects from Kinvoke CGNet, which attaches eBPF programs to containers or pods, and it gathers the network stats from the pod and then pushes it to Prometheus, which can, so this is a great way of visualizing network stats per pod with minimal overhead. So in a host where we have access, where we can log in into the system, we have an easy way of deploying these tools, install the dependencies, but how do we deploy it in Kubernetes? So we do it the Kubernetes way, of course. So we run a privileged pod, which shares the host PID, and the volumes that is required in that pod will be lib modules and proc, so that it has access to the kernel symbols and the processes running in various containers in the host. We can expose HTTP endpoints, which can be hit to collect particular matrices. So let's go through demo. So what I have for the demo is a cluster that is deployed using Gardener. For the first demo, what we'll be doing is we'll be generating a off CPU time flame graph for the processes running on the host. So for example, Tom has a Postgres instance running in a node inside a pod, and he is using another web app to use that Postgres instance in another pod. And he sees that there's some lag or latency in the system. So he goes to Bob from operations, and then he asks him, okay, there's some problem with the instance. How do I figure out where the problem is? Bob looks at the dashboard and says, okay, there's a CPU, high CPU utilization, or the process, or the particular process is consuming this much of CPU. But Tom still doesn't have an answer that what is wrong with the process running, why it is taking so much of CPU, or details like that. So what Tom can do is that he can deploy this BPF tools in a pod and then query those HTTP endpoints to gather particular specific detailed matrices from the system. So here I have two. Oops. I did. Yeah. Okay. Great. No, I can't see it. Okay. Just a second. I think this is done. Okay. Yeah. Yeah. Just a minute. Thank you, Prashant. Okay, so good. So here I have two terminals. In one terminal, I'll be logging into the PG Postgres instance and running a benchmark tool, PG Bench. And in a second terminal, I'll be running the off CPU time tool that will collect the off CPU time and generate the flame graph for it correspondingly. So what I'll do is I'll start. So this is the URL that is the load balancer service URL, which and the off CPU time tool is exported on this endpoint. I'll run this tool for 10-second duration and expect the output in the flame graph format. And on another terminal from the Postgres instance, I have launched the load for Postgres. And let's see what this off CPU time flame graph looks like. So here, okay, so I was maybe just a minute. Okay, so I'll start the collection again because there was some delay before I was describing about the tool and I started the load. So I'll just keep running the load until it collects the data. Yeah. So here we see the Postgres process showing up. Okay, so there are a lot of unknown symbols. What I'll do is I'll start this gathering again. So what off CPU time this tool does is that it traps or it traces the scheduler process of the Linux kernel, and whenever the scheduler schedules out any process, it saves its stack and saves the time at which it was scheduled out. And whenever that process is scheduled back into the system, it calculates the time difference for which this stack was off the CPU, and it keeps aggregating that data in the kernel, and which is read from the user space, and that data is fed to the flame graph tool that I talked about earlier, and then it sends the data to this back to the requester. So here we see that the Postgres process spent most of the time off the CPU because it was running this function pqflush. So details like this we can gather, and similarly there is a Java pod that is also running. We can get details like this that we saw earlier, the two threads, the light thread and the heavy thread, and why they were scheduled off the CPU. We see that sleep here again because why it was scheduled out. Similarly, I can also use these eBPF tools for security purposes. What I want is that whenever someone logs in into the node or the Kubernetes node, I generate an alert. Maybe some siren goes off somewhere. Maybe I get an SMS or a call. So what I'll be showing here is that I'll try to log in the node, and what I'll be expecting is a call on my phone that says that there was a login attempt on the node. So yeah, let's do that. So this is a pod from which I'll be logging in, and what I am expecting is a call on this phone here. Soon. Yeah, here it is. So when I pick this up, what it says is
there was a login attempt.
Here it was. I hope it was audible. So these kind of alerts can be generated. What it does is whenever someone logs in, the handler is called, which submits an event to the user space, and the user space component handles that event asynchronously, makes the call to the number provided, pre-programmed number provided in the tool chain. Now, this tool can also be used to log what the host is doing. So someone was able to log into the system. Now I want to log what that user was doing on that PTS device that it opened. So for that, I can run this another tool, TTY Snoop, and log whatever was happening on that particular character device. So I'll run it for 20 minutes duration, but this can as well be triggered when someone was able to log in into the system. So here we run this, hit the endpoint TTY Snoop, which starts recording what the user was doing after logging in. I'm doing some random steps in the terminal above. Something, and after the duration of 20 seconds, sorry. After the duration of 20 seconds, I see that whatever the user was doing after taking the shell terminal is duplicated, or I get the log of what that user was seeing. Now this can be utilized to replay what the user did and what the effects were of his actions. So this was the demo of generating off-CPU flame graphs on the demand, generating alerts when someone takes a shell logging or monitoring a PTS devices. These are some of the references that I had used. Okay. Yeah. Thank you for attending the talk. Any questions? Thank you very much.
So I understand that you can use this to intercept syscalls and all, but can you actually modify a given call?
Can you?
Modify a call. Could you actually intercept and modify something that happens?
Okay, so the question is that you can trace the calls, but can you also modify based on what the call is doing? So yes, BPF also provides BPF actions. Based on that, the parameters can be modified or can be dropped. It doesn't necessarily have to go through the whole process.
So I've tried to do something similar about kind of streaming back the session, but I couldn't work out how to or where to hook into the system to firstly know when a new session has started, and secondly what to use to track the session. So what kind of BPF hooks are you using to track the session itself and keep streaming the output back?
Okay. So I believe the function's name is tty-write from the kernel. Yeah. And it gets all the data that is being written on the terminal, and that data you gather either in the kernel maps, or you submit an event for it, which can then be handled from the user space component and can further be saved in data structure, which can be returned back. So I believe tty-write is the correct function, but any other questions? Thank you very much. That was